Hi again and welcome. In this video what I'm going to cover is acceleration, and if time permits I'll talk about kinematic equations. So after talking about speed and velocity, we saw that speed is basically how fast something's going, and velocity is a little different because it gives you an indication of the direction of the object. So typically not all things maintain their speed, so when they do, they undergo an acceleration. So an acceleration by definition is a change in velocity. And since we're changing our velocity, which has direction, it makes acceleration a vector. So it's a directional piece as well. Okay, so acceleration, and although again the sign of average is here, we usually ignore it. Acceleration is a change in velocity over time. So I actually like to rewrite it like this. In fact, I'll even write it as A equals Vf minus Vi over time. As you might imagine, this is a change in velocity, so we need a final velocity and initial velocity to undergo a change. Now something about this too is that since we're changing our velocity, that can include magnitude or direction. So I can change my speed, so it can be something from like 0 to 40, that would be a change in magnitude, or the vice versa. I can go from 35 to 15. These will all be changes in our velocity because we're changing our value. Regardless if we speed up or slow down, it's an acceleration. So yeah, sometimes you see the word deceleration, but it's still considered an acceleration because we're changing. So it's the change that makes it an acceleration. Since velocity also includes direction, anytime you have a directional piece, you will undergo an acceleration. So one of the best examples is an object going in a circle. That's because the direction is constantly changing, because the direction here is straight up, but at this point, it's pointing this way, etc. like that. So changing direction changes your velocity. It's a little delta there. Delta for change like that. Okay, so acceleration also has interesting units, so it's how fast per second. So since this is in the bottom of our fraction, we can actually combine this to make this meters per second. So both of these are actually acceptable uses for units, but usually we write it like this because it's a little more compact. This is pretty cool. It's an in-class demo where we measured the acceleration of a car going really fast, but we're going to skip that for now. Okay, so here's a sample problem. A car slows down from rest, from 23 meters per second, so I'm going to kind of do that, to rest. Now, even though this is not a number, it does represent a number of 0. So this is technically embedded right there. And this is our time. So I like to underline and highlight my information and take it out of the problem because all those words can kind of be confusing. And then the question is, what is the car's acceleration? So what we're going to do is we're going to list all of our information. So my initial velocity starts from 23 because it says it slows down from. So that's going to be my initial. So it goes to rest. That means that's going to be my final velocity like this. And to do that change, it took 7.39 seconds, just like that. With the question being the acceleration. So the equation for acceleration is Vf minus Vi over t. So I'm just going to move this over. If I go ahead and plug this in, A is going to be my final velocity, which is 0, minus the initial, which is 23. It's very important that you walk through this step because sometimes you will see this and automatically think 23, which is a good shortcut, but in this problem we actually need to take into account the direction, so this negative sign matters. And then I'm going to plug in the 7.39 seconds like that. So let's go ahead and calculate this. You can see that this is negative 23, because 0 minus 23 is negative 23, over this. Gives us 3.11 negative meters per second squared. Okay, so what does this mean? So this means we're changing, so the number means how much we're changing our velocity by. So this is the value of change. All right. Now, the negative means opposite of motion. So the negative doesn't always mean slowing down. It just means it's going opposite what we defined as the positive motion. But if you notice, we're going positive to begin with because we're slowing down from that. So basically, if I draw the vectors of the car is moving forward starting at 23, but is experiencing the acceleration this way. That's what that negative side means. And then when you have a case like this, when your motion is forward but your acceleration is opposite, you're slowing down. And to check if this is true, we read the context of the problem, and it is. It literally says slows down. So you can't see acceleration. So that's a big thing. You can see motion, but you can't see acceleration. Oops, I'm sorry. Velocity, my fault. You can see your velocity, but cannot see acceleration. So when it comes to visualizing this, this is what you're seeing, this is what you have to imagine. Because you don't actually see something pushing you in the opposite direction when you're slowing down, but you have to imagine it. So that's a pretty straightforward example. So this is what I was talking about when I came to talk about acceleration and slowing down and speeding up. So when you have an object, its acceleration and motion in the same direction, it's going to speed up. And then when they're in the opposite direction, the object will slow down. And this is kind of a fast forward, but when you have an object that goes around in a curve, the acceleration points to the center, and you can notice that right here. See how it points to the center? Very quickly. So there are some rules, if you will. And here they are. The rules are the following. If there's no acceleration, then that means the object's not changing its motion, so it's moving at a constant rate. Positive means you're moving forward, and negative means you're moving backward. So if you're both positive, both the acceleration and your motion, then you're speeding up, moving forward. If you're moving forward but your acceleration's backwards, and you slow down while moving forward, and vice versa. If you're moving backwards but the acceleration's forward, you're slowing down, but your motion comes from this sign, which is backward. And then vice versa. You can be speeding up backwards if your direction is backward and your acceleration is backward. So you could be moving faster backward. So it's like if you start backing out of a parking spot, you speed up. So that's an example here. Slowing down backward is you stop to make a K-turn during that. And then this would be an example of a car starting at rest and moving forward, and then this is, of course, coming to a stoplight. So those are all examples of things that have these types of motions. Okay, and then at this point, we're going to introduce what we call the kinematic equations. So basically, we're taking time, acceleration, position, displacement, and velocity, and giving us a method to solve problems. So we have 4 different kinematic equations. Turns out in physics you can solve things however you want. So there's multiple ways to solve your problems, but some of these are better than others in certain cases. So delta x represents a displacement. Vi is our initial velocity. Vf is our final velocity. And our A stands for acceleration and T for time. So notice that this equation is good, but has no acceleration in it. This equation has no position, no time, and no final velocity. So in all of these cases, you can use any of these equations at any point to solve problems, but you might run into issues if you don't have position while using this, or vice versa. So let's take a look at how to use them. So if you're not used to solving word problems, I recommend you go through this process. Read the problem, naturally, and you might have to do this 1 or 2 or even 3 times to really understand what's going on. And in this one, the other thing is to analyze your information. You know, sometimes they give you more numbers than you need, so you need to figure out what's important and what the numbers actually mean. Is it something that you need? And then reword the question for understanding. So, you know, I like to draw a picture to make sure I understand it, or try to, you know, map it out with something to make sure you understand it. Extract knowns, get the unknowns. That's going to give you a visual of which equation to choose and then to solve. And then, of course, making sure that your answer makes sense. So, and this is basically some other notes you can read on your own. Let me solve 2 problems for you here. Okay, so the first problem says, coming to a stop, a car skids on the highway. Assuming that the deceleration is this much, what is the initial speed of the car before braking? Okay, so first I'm going to analyze my problem. So it says, in coming to a stop. So this is going to be, because of the way this is phrased, in coming to a stop, that's my final velocity, which is 0. Car skids that far on a highway, so it's going to be a displacement. Now, since it didn't specify a starting point, we can assume it started at 0 and then go with the 92. Next, we have a deceleration, so it's slowing down. So this represents an acceleration. But since it's going to be going opposite, since we're slowing down, we have to throw in that sign. That's not always the case, but this is the case here. And again, the reason I'm throwing in the sign is because it's slowing down. So it's moving forward and coming to a rest. So it's coming to a stop. That tells me the negative sign has to go here. Question is, what is the initial speed? So when I see this, it wants a value. It doesn't care about direction. If it said velocity, then we'll have to pay attention to signs. But, I mean, the answer is just going to tell us what's going on anyway. Okay, so a car comes to a skid. So it looks like I'm going to run out of my time here. So let me just label everything, and then the next video I'll describe how to solve this. Oh, sorry, we know that's 0. So I'm diagramming this problem because it's just so much nicer sometimes to see what's going on. And then I'll put, doesn't matter where I put it, I'll put the acceleration here. Like that. So I'll solve this in the next video.